Hi, good morning. Um, I'll be recording chapter 2, which is Chemical Foundation of Life this morning. Now, it is, I told you I'm going to be making the video as short as I can. So that means there are some parts I may not focus on, and the part I'm not focusing on will only mean that it is self-explanatory and not that it is less important. All right. So, chemical foundation of life. We'll be looking at matter, elements, atoms, isotopes, ions and molecules, water and carbon, and few other. You should be able to identify and explain, give examples, understand the concept of all of this. Now, organization of living things starts from atom, it goes to molecule, it goes to macromolecules. When you talk of molecules, you are talking about elements that are formed together: chlorine molecule, hydrogen molecule, helium molecule, lithium molecules. Those are molecules. Then macromolecules are formed from the elements, right? Now, macromolecules range from your protein. Macro means it is big. So it ranges from your protein, your lipids, your carbohydrate, and nucleic acid, RNA and DNA, right? Those are macromolecules. Then organelles. I told you yesterday, organelles, they are the small organs inside the cytoplasm that are suspended in the cytosol, right? The cytosol is the liquid that is in the cytoplasm. Then the cell is the next one, the tissue is the next, organ is the next, and organ system is larger than organs. And I told you the difference between organ and organ system is organ is your heart. Organ system is cardiovascular system. Organs are subset of organ system. So your heart is an organ, is a part of the cardiovascular system. And cardiovascular means cardiac, which is a heart, and vascular, which are blood vessels. So that means there are some organs that make up the cardiovascular system. Heart is among it, blood vessels, artery, veins, capillaries, they are also part of the cardiovascular system. Then all of those systems coupled together, working together: urinary system, digestive system, respiratory system, reproductive system, lymphatic system, muscular system, skeletal system. All of those systems working together gives the organism, right? Okay, so let's go. Now, an atom, a matter rather, is anything that has space, anything that have mass and occupy space is a matter. So you have mass, you occupy space, you are a matter. My phone has mass and occupies space, it's a matter. This bottle of water has width, it has mass and occupies space, it's a matter. The computer I'm using now has mass and it also occupies space, is a matter. Then elements, the elements are substances that have atoms that have the same number of protons. Now, so I would still talk about this over time as we go, but you will have heard of first 20 elements, which is a common one. It's hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. Those are the first 20 elements I just sang. I learned that song like about 15 years ago or more. So those are elements, and each of those elements, they have a specific number. We call it proton number. It's going to also be the same as atomic number, but we'll be talking more about it. Now, the proton number will be the same for every element. So there's no element that can have the same proton number with another element. Proton number is unique, is distinct. It's like your fingerprint. it does not change for an element. So a specific element has a specific proton number. The unique thing about elements, again, is that they are simplest. They cannot be further broken down. Now, what is an atom? An atom is the smallest unit of matter. Now, both it must be able to retain all of the matter's chemical properties, all of the chemical properties of an element. Now, the same thing, a cell is the smallest and functional unit of living thing. Now, but a cell, for it to be considered a cell, must have all the characteristics of living things. That's the same way. So as a cell is to living thing, that's the same way atom is to matter. Atom is the smallest unit of matter, but it must contain all the chemical properties of an element. Now, every element has a name and an atomic symbol. So let's go. This gives you the normal distribution of some elements in living organism. You have oxygen, carbon, hydrogen, and nitrogen. You can say they are percentage. These are macro elements. I mean, these are elements that dominate living organisms. Now, when you see an atom has, oh, I wish I can clean this now. An atom has 3 components. It's made up of protein. It's made up of proton. It's made up of electron. And it's made up of neutron. So I can say atom is made up of pen, or an atom is a pen, right? You know, it's proton, it's electron, and it's neutron. Now, proton and electron is what makes it located in the nucleus. Proton and electron is located in the nucleus, and that is what forms the mass number. That's what determines the mass number or atomic number. So you can call it mass number or atomic number. That's what usually we'll say atomic number because we are talking about an atom, but it's still their mass number, right? So it's what determines the mass number. Oh, I can't write beyond it. So it's what determines the mass number of the atom. So neutrons, you can see, and proton, they are located in the nucleus. And the proton is a positively charged substance. It's positively charged, and the neutron is neutral. So neutron is neutral. I'll just put N as neutral. This is positively charged. And the electron, which I'll be talking about, is negative. Now, I told you the proton and neutron is inside the nucleus, and that's what determines the width of the atom. But electron, on the other hand, just revolve around this orbit. You can see it just revolves around the orbit. So the electron does not determine the width of the atom. Now, usually, I told you earlier that this proton is what determines the uniqueness, is the fingerprint of all elements. Proton is the same as atomic number, all right? So proton and atomic number, proton is equal to atomic number, is the same, all right? Now, proton is the same as atomic number. Now, generally, for a neutral atom, don't confuse it, a neutral atom, electron and proton can have the same number. For a neutral atom, electron and neutron can have the same number, but neutron can be different and it may be the same. I'll still be talking about it. I'm just laying the foundation here. For a neutral atom, when I say neutral atom, it means an atom that doesn't have any charge on it. When an atom becomes a charged atom, we call it ions, I-O-N. That is when an atom becomes charged. Something like Cl minus, it is carrying the negative sign. It is an ion. Such as Ca, this is calcium, 2 plus, it is carrying ions. It is carrying charges, right? So it is ion. So ions or ion, they are atoms with charges. But atoms that doesn't have charges, it will have the same proton and electron number. Now, why is that? Proton number and electron, proton is positive, electron is negative, so it can balance up. That's the ideal. When it balances up, when it's at equilibrium, then the atom is a neutral atom. But when one is more than the other, or one is less than the other, then it will carry a charge, either a negative charge or a positive charge. The moment it carries either of those charges, it becomes an ion. It will no longer be a neutral charge, right? It will no longer be a neutral atom. Now, so that tells you that, again, for neutral atoms, electron and protons have the same number. But neutron can be different and it can be the same. But for ions, electron and proton, we have different numbers. Again, neutron can always be different. And don't forget, neutron plus proton gives you the atomic mass or the mass number. Let's go. So now, atomic number. All atoms of an element have the same number of protons, I told you, right? An atomic number is the same as proton number. Don't confuse it. Atomic number is the same as proton number. This is atomic number. This is number of proton. It is the same. Can you see? All atoms have the same number of protons. Atomic number is the same as proton number. I don't want you to confuse it. That's why I'm saying it again. Now, for a neutral atom, the atomic number, which is the proton number, also tells you the number of electrons. But when the atom begins to have charge on it, when it is no longer a neutral atom, then the number of electrons will be different. I hope you understand. If you have questions, please send me an email. Now, the mass number, what does it depend on? It depends on the number of protons and the neutrons. I told you, the neutron and protons they are located in the nucleus. Electron revolves around it. The neutron, the content of the nucleus, it was determines the mass number, right? So, looking at this, atomic number is 6. Atomic number is 6. Then, what is going to be the proton number? Proton number is going to be 6 as well, right? Because it is the same as atomic number. For this compound, for this element that have the same, that doesn't have any charge, what is the electron number? Electron number is 6 as well. But look at it. Something is different. This is the mass number, 12, for this carbon. This is the mass number 13 for this carbon. Now, when we begin to discuss isotope, mass number can be different because neutron number can be different. Does that make sense? Because now, mass number, which I would use as m, is equal to neutron plus proton. So, since these can be different, that means mass number can also be different. Now, this neutron can be different for the same atom, right? Now, so I'm going to talk about that. So look at this. I'm talking about what makes neutron to be different. This is the atomic number. This is the atomic number. Two different types of carbon, but their atomic number is their fingerprint. It will always be different. But their neutron is not their fingerprint. Neutron can be different. Now, if I had shown you earlier that mass number equals proton or neutron plus neutron, what does that mean? So here, proton is 12. Then, so I'm going to do it like this. That means if I want to get the number of neutron, neutron can also be mass number minus proton. Do the calculation whichever way it interests you. So for carbon 13 now, for this carbon now, that means the neutron is going to be 13 minus 6, which is going to give me 7. So proton number for this carbon is 7. Whereas for this carbon, proton number is going to be, neutron number is going to be, neutron rather, not proton, is going to be 12 minus 6. And so the neutron is going to be 6. Does that make sense? So the neutron is 6 here. So that means for this carbon now, neutron is 6, proton is 6, and electron is also 6. Does that make sense to you? For this carbon, because every carbon is going to have a proton of 6. Proton and atomic number is the same thing. Every carbon is going to have a proton and atomic number of 6. But because it's a neutral carbon, it has electron of 6 as well. And when we do the calculation now, we also saw that neutron number is 6 as well, because 12 minus proton number is going to be 6. But for this other carbon, we can see that even though they have the same atomic number and proton number, which will always be the same for every element, every particular element have a fingerprint, and the fingerprint is the atomic number, so it's 6. But it has a different mass number. If it has a different mass number, it means it has a different neutron. And I told you, neutron can be different. It can be the same, and it can also be different. So the neutron number is different. Now, this type of carbon that have two different strains, we call it isotopes. So now looking at this, what is an isotope? Isotope is a single element that have the same atomic number but different neutrons. You can see neutron is different. So isotope, they have different neutron. Neutrons is different. That's the difference. So when you think of isotope, think about these two carbon I have on the screen. The same atomic number, but different neutron number. That is an isotope. And obviously, if they have the same neutron number, if they have the same proton number, but different neutron number, then they are going to have different mass number or atomic mass. Does that make sense? Thank you. Don't forget, atomic mass is the same as mass number in this case. So look at this. So looking at this now, these are 3 different isotopes of carbon. These are 3 different isotopes of carbon. You can see this is carbon with different mass number, meaning that what's the number of neutron here now? We know that all carbon has 6 protons, but the neutron here is going to be 12 minus 6, that's 6. The neutron here is going to be 13 minus 6, that's 7. The neutron for this carbon is going to be 14 minus 6, that is 8. So these carbons have 3 isotopes, and we say this is a stable isotope. This is also stable, but this is unstable, it is radioactive. All right, let's go. So radiocarbon dating. Now radiocarbon dating is simple. It's getting the date or age of an element using carbon. Now, all they do is this: they check the number of the ratio of carbon 14, which is the isotope that is not stable. You remember, which is the isotope that is not stable. They're going to compare the ratio of carbon 14 to the ratio of carbon 12. Now, that is what they use to compare the age of an element. And you know, carbon 12, because it's not stable, it will keep decaying, but carbon 12 will not decay. Carbon 14 will be decaying because it's unstable. Carbon 12 will not decay. Okay, so let's just go through that. Now, this is what I've been talking about when I say elements. These are the elements that we know. An element, you can see they are arranged in the periodic table. This is group 1 element, this is group 2 element. You have the group continuous like that. Now, usually in the lab, when we talk about groups, we call this one group 1 element. We say this is group 2 element. We call this group 3. We call this group 4. We call this group 5. We call this group 6. We call this group 7. We call this group 8. Now, it doesn't matter. Because if you take note too, this is both 3 and 13. So it's all ends in 3. This is 4. This is 5. This is 6. This is 7. So it continues that way. So they are both like corresponding. But usually in the lab, we don't really talk about you. It is in rare cases you use this element in this group. Obviously, we use zinc, we use copper, nickel, but it's not as common as this and as this. I'm messing up this slide a lot now. But what I want to show you here, this was the first 20 elements I sang in song the other time. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. Now, as they have their unique atomic number, and they have their unique atomic number. Is the same as their proton number, right? Then electron number can be the same as it is now. The electron number and their proton number are the same because they are neutral atoms here, neutral elements here. They don't carry any charge here, right? So their electron number and their proton number are the same, but their mass number will be different. Obviously, their neutron number also can be different. So these elements, they are group 1 element, they are group 2 elements. Then this tells the rows tells the period. So we say this is period 1, this is period 2, this is period 3, this is period 4. Majorly what we use to determine their properties is the group where they belong. But let's see, we'll talk about a few of them as we go. Now, an atom's electron shell can be modeled, and I'll be talking about how to do the electron shell. When we say electron shell, we are talking about something like this. I'll be describing how it is, how it helps chemical reaction, its relevance, and its importance. So let's go. Now, for the 20 elements that I talked about, which is hydrogen up to calcium, this is number 20. It means their number on the periodic table is also their atomic number. It's also their proton number. So number 1 is hydrogen. It has proton number of 1. So if you know the first 20 elements, it means their number is their proton number. So number 18 is argon. So it means the proton number is 18. Number 20 is calcium. It means the proton number is 20, right? So that is how it is. Number 11 is sodium. It means the proton number is 11. The atomic number is 11, right? And if it doesn't carry any charge, it means the electron number is still 11, right? Good. But it has a mass number of 23. So it means the atomic number, the neutron number is 12, right? Good. So let's go. Now, I'll be talking about this, and I wish I can use my board now. But this is the first time I'm trying this out. I don't think I want to risk it, since I'm not sure you will see it. Now, when we talk about electron shell, it is simple. I told you that every atom have a nucleus, and the nucleus is what houses the proton and the neutron. Then I told you electron revolves around the orbit like this. So you have electron revolving around. So here, this is the nucleus. This is where you have the proton and the neutron. They are right inside the nucleus. But electron revolves around. So electron creates an orbit. It creates a cycle. It creates a shell round about the nucleus. Now, how do we distribute the electron? That's what we want to look at. That's what we call electron shell. How to distribute the electron shell. Now, the first thing I need you to take note about electron shell is that this inward shell, this is the first shell. This shell is one end, right? And end so this shell is one end. It means it is one. Now, where I'm going is this shell can only contain 2 electrons. And it is the same for every cell. Now, for every element, it can only contain 2 electrons, means that the maximum it can contain is 2. So this first shell cannot take more than 2 electrons. We are looking at electron distribution. So let's say that sodium, it has 11 electrons. Now in my mind, I know that the first shell can only take 2. The second shell can take 8. And the last shell can take 8 if it has the last. Now, the number of electrons determines the number of shells that an element is going to have. So an element that have 11 electrons like sodium is going to have 3 shells, because the first shell can only take 2. But every other shell can take a maximum of 8. They cannot take 9. They can take 7, they can take 6, they can take 5, they can take 4, they can take 3, they can take 2, they can take 1. But they cannot take more than 8. So the first shell can take 1 as well, but it cannot take more than 2. The second shell can take 8, it cannot take more than 8. The third shell can take 8, it cannot take more than 8. Every other shell, the third shell can take 8. The 20th shell can take 8. Every other shell after the first one can take only 2, can take 8. So think about it. The first shell, the maximum it can take is 2. It can take 1, but that's the maximum, 2. But every other shell outside the first shell can take 8 electrons. Does that make sense? All right. So for sodium that has 11 electrons, that means the first shell is going to take 2. The second shell is going to take 8. How many do we have left? We have 1. That means the third shell, we can't throw it away. We have to create a shell for that one. So the third shell is going to take 1. So if I want to draw this now, for sodium, this is what I'm going to have. The first shell has 2, you can see. The second shell has 1, 2, 3, 4, 5, 6, 7, 8. And the third shell have 1. If I want to write the electronic configuration to make it easy for me, then sodium Look at it. Sodium is going to be, oh, see the way I'm writing. Now, sodium is Na, right? Then equal to, what is the number of electrons in the first shell? 2. I'll put a comma. What is the number of electrons in the second shell? 8. I'll put a comma. What is the number of electrons in the third shell? 1. 281. So 281 tells me the first shell has 2, the second shell has 8, the last shell has 1. And for like calcium, that is number 20. Even without doing the shell, the diagram, if I want to use this model to determine how the diagram is going to look like, I can do that before I even do it. Then it's going to be 2. Then the next one is going to be 8. I have 10 already. I need 10 more. Then the next one is going to be 8. How many do I have left? Calcium is 20. It has 20 electrons. 20. This is already 18. Then I need 2 more. That is, so calcium is going to be 2. First shell is going to have 2. Second shell is going to have 8. Third shell is going to have 8. And the last shell we have 2. I believe it makes sense to you. Okay, so atom will give up, accept, or share electrons in order to have 8 electrons. Now look at it. This atom, chlorine, has 1 electron here. This shell can take a maximum number of 8, but it has just 1. Is it balanced? No. Is it stable? No. And that is why you see that sodium is always in most of chemical reactions that you see, because it is an unstable element. It is unstable because this shell is able to take 8, but it only has 1. Now, what will make sodium to be stable, what will make generally every electron to be stable, is when their shell, their last shell, is totally filled up to become 8. So that means, look at this, that means compounds that are stable is going to be these compounds that are here. These are stable elements. Helium is stable. Why? Because it only has 2. So it's going to be like this. This is the nucleus, and number 1 is going to be here. Another electron is here. So it's stable because it's supposed to have 2 here, and it has all the 2. Neon is number 10. It's stable as well because it's going to be 2. First shell we have 2, second shell we have 8. So it has 8 outside. It's balanced. Argon is stable too because it's going to be 2, 8, and 2. So, and 8. Number 18, right? 2, 8, that's 10, plus 8, that's 10. That's 18. So it is balanced. So all these elements here, you rarely see them. And look at it. Go and look at chemical reaction. You may not notice helium, neon, argon in chemical reactions because they are stable. They are noble gases. We call them noble. Noble because a noble person is someone that is wealthy, is doing well. It doesn't need other people to survive. So that's the way those elements are. We call them noble gases. Noble, N-O-B-L-E. They are noble gases because they have what they need. They don't care about others. They have what they need. They don't need other people to survive. They don't need to engage in chemical reactions because why do elements engage in chemical reaction? Is to become stable, but they are stable already. You know, sometimes you relate with people because now, how do we have a relationship now? The reason I have a relationship with you is because you want to learn something. So, but by the time you learn it now, you may not even thinking of reaching out to Mr. Hey after the summer semester because you don't need me again. You are noble, right? You already got what you want. And so all these elements in group 8 or group 18, they are noble gases because they already have what they need, so they don't involve in chemical reaction. But other elements are usually interested in chemical reaction because they want to be complete. Now look at sodium. Sodium is not complete. It's not stable. So you will always see sodium relating in chemical reaction. Now let's go to this. This is lithium. And you remember on the periodic table, what number is lithium? Hydrogen, helium, lithium. So that means lithium is number 3. It is number 3 on the periodic table. That means it has a proton number of 3. Right? Now, if it has proton number of 3 and it's not a charged molecule, it's neutral, that means it has electron number of 3. So, and I know the first shell takes 2, then the second shell is going to have 1. So we have 3. Now, this is the first shell, it has 2. Then second shell has 1. That means it has 1 outside. What did you take note? You notice that sodium also have 1 outside. That tells me they are both group 1 element. Let's go back to the periodic table. Can you see? This is lithium and this is sodium. So group 1 elements, we always have 1 on the outside. Group 2 element, we always have 2 on the outside. Group 3 element, we always have 3 on the outside. And group 8 element, we always have 8 on the outside. You can see how it connects. All right, so let's go back to our slide. So this element is not stable. And how will it be stable? I will be talking about that later. So this is still the same discussion, showing you that this is group 1 element, hydrogen, it will have 1 outside. Group 1 element, lithium, it will have 1 outside. This is sodium, it will have 1 outside. You can see. So elements in the same group have the same number outside. Group 1 have 1 outside, group 2 have 2 outside. This is group 4 now. It's going to have 4 outside. Now this is group 4, which is the same thing as 14, right? It's going to have 4 outside. Group 17, which is 7, is going to have 7 outside. 8 is going to have 8 outside. Now, these are noble gases. These are balanced. They don't involve in chemical reactions like that. Now, both this is not balanced. This is not balanced. This is not balanced. And I'll be talking about it in a bit. Let's go. Now, chemical reactions. I told you that the reason that elements engage in chemical reaction is to attain a stable nature. And when I talk about stable, stable is the same thing as balanced. Is also the same thing as octet. Octet means 8, meaning that they want to have 8 in their outermost shell. They want to have 8 electrons in their outermost shell. Before I continue with this, I want to show you valence number. Look at this. Then I'll come back to that. Now, the last shell is the valence shell. Any shell that ends the electron shell is the valence shell. So this is not the valence shell because it's not the last one, but this is the valence shell because it's the last one. Now, the number of electrons on the valence shell is the valence electron of that element. Does that make sense? All right. So when you talk about valence number, okay, let's go. Valence electrons are the number of electrons on the valence shell. Makes sense, right? Let's go now. Now, chemical reaction happens so that electrons so that elements can become stable, they can become balanced, they can become and they can attain their octet stage. Now, look at this. This is hydrogen, right? And this is hydrogen and this is oxygen. What number is oxygen on the periodic table? Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. So that means oxygen is number 8, right? Good. If oxygen is number 8, the first shell is going to take 2 and the second shell is going to take 6. 8, 2 plus 6 makes 8. Now, you can see the first shell already have 2. That's not drawn out for us because what we need now is the second shell. And the second shell have 6. Now, let's count. 1, 2, 3, 4, 5, 6. Take note of the way it is written. They are drawn. You can see that you have 2 here, you have 1 here, you have 1 here, you have 1, 2 here. You take note that it is not like this. It is not. It has 6, right? You know it can be done like this. But it wasn't done like this. That is deliberate. The reason is this. This is the way to fill it. I know I have 6. Then I'm going to fill it like this. 1, 2, 3, 4, 5, 6. Because we are interested in the number of unpaired electrons. Now, so there's a rule that says you fill single first. You fill single. An element has 6 on the outside. You are not going to put all the 6 together at once. You are going to fill single. 1, 2, 3. Don't forget the electron are revolving, right? 4. We have 4. We need 2. We need 2 more. We are going to fill single before we double them. So now, let's double them. 7. 1, 2, 3, 4, 5, 6. So now we have 2 electrons that doesn't have a partner, that are not paired. Those are the electrons that are interested in chemical reactions because they have to be paired. All right? It is when electron pairs together with electrons on a different element, that is how they bond together, and that is chemical reaction. So let's see how hydrogen is going to bond with with oxygen. You know, this is water. We want to form water molecule now. So you can see this is one hydrogen here. This is one hydrogen here. This is oxygen, and this is another hydrogen. There is one oxygen has 2 electrons that are not paired. So if I ask you, the number of unpaired electrons in oxygen is actually 2. Right? This is unpaired. This is unpaired. These are paired. Paired, P-A-I, right? These are doubled. These are doubled. These are not doubled. They are single. So these need to be doubled. And when these become doubled, that's when oxygen will become balanced. So what is going to happen? This electron here for hydrogen, you know hydrogen is number 1, so it has 1 electron. Is going to couple with this. They are going to share it together. All right? And that's what you see here. They are sharing it together. It is not, hydrogen did not give it to oxygen. It is sharing it with oxygen. Now, think about it. You have a sandwich. You have a sandwich, and I have orange juice. We want to eat. We are both hungry. Orange juice will not satisfy my hunger. If you eat your sandwich too, you want a drink. Then you just come, you say, let's share together. Mr. A, let's share together. And you brought your sandwich. We cut it into half. I brought my orange juice. We divided it into half. We had it together. Both of us have orange juice and sandwich. Both of us had food. Right? So we share the food. I didn't give you mine. It's not like I sacrificed mine to you. No, we both shared. Right? Right? Sharing is caring, right? So they are sharing. And sharing is fun. So they are sharing it together. And I'll be talking about that because that is very important. And you can see another hydrogen is here too. It shared with these as well. So they formed a bond together. So here you can see these are shared with this, and these are also shared with this. Now, when we want to count the number of electrons for hydrogen, how are we going to count it now? Look at it. This is number 1, and this is number 2. So now, hydrogen that used to have 1 electron in its first shell, and the first shell can take 2 electrons, you remember. But hydrogen was not stable. It needs 2 to be complete. So to be stable, so it partners with oxygen to share electrons together. So now, when you see hydrogen, you are not seeing an hydrogen that has 1 electron. You are seeing an hydrogen that has 2 electrons by sharing with oxygen. So, like myself sharing sandwich with you, you are seeing Sheol now. We are seeing Mr. Hay that doesn't just have orange juice, but has orange juice and sandwich by sharing with someone. Does that make sense? Good. Now, so that is what sharing is. Now, look at this. Let's count. So the same thing for this hydrogen, the same concept, right? Now, let's count for oxygen. If you want to count the number of electrons that is associated with oxygen now, it's going to be 1, 2, 3, 4, 5, 6, 7, 8. So oxygen is balanced as well. Now, look at one thing that is key. Now, how many electrons does hydrogen have originally? Hydrogen have 1 electron, but now it has 2. Now, before, this hydrogen here, let me use another color now. This hydrogen here, I'm going to pick green. All right, this hydrogen here, it used to be normal H. It doesn't have any electron, it doesn't have any charge on it. It's H. The hydrogen here too is H. But the hydrogen here, it's no longer the ordinary H. Now, it has become H2O, which is water molecule. And what does that mean? It means that the hydrogen here is sharing electron with the hydrogen, with the oxygen here. All right. So if I want to break this down now, H2O, if I want to break it down, it's going to be, I have 2H plus oxygen. Does that make sense? 2H plus oxygen. Now, does that make sense to you? Good. I'll be talking about an aspect later. I don't want to go to it now so that I don't confuse you. But if you have questions on any of those slides, just send me an email. Ask me. Now, this is a bond. And that should tell you something. How many electrons do we have here to form this bond? 2. There's a contribution from hydrogen. There's a contribution from oxygen. The same thing here. There's a contribution from hydrogen. There's a contribution for oxygen. So we need 2 electrons to make a bond. When elements shares electron to form a bond, we call that kind of bond covalent bond. So the kind of bond we have here, that hydrogen and oxygen are coupling together to achieve what they don't have, balance. Hydrogen used to have 1 instead of having 2, so it's not balanced, it's not stable. Oxygen used to have 6 instead of 8 is not stable. So 2 hydrogen coupled with oxygen to become, so that both of them can be balanced. That kind of reaction is called covalent, cooperation, covalent. They are covering up for each other. They are cooperating with each other. They are coupling with each other. So covalent bond. All right, let's go. Now, covalent means covalency. You remember I told you that valence electron are the electron outside, right? So they are covalency. They are covalencing together. They are cooperating together. All right, let's go. Now, so this is the same. Now just look at it, right? Chemical bond, they form a bond together now. They became good. That's what I was trying to show you there. 2H plus O gave you H2O, right? That's what I have here. H2H plus O. Good. Now, this is water molecule. This is a water molecule that is formed here. It's a water molecule. A water molecule is formed. It's the smallest part of a compound that still has the property of a compound. So this is the smallest way water can appear. Water cannot be simpler. It can be larger, but this is water. So you can have 2HO2. You can have 3H2O. So, but this is a molecule. This has become 2 molecules. This is 3 molecules, right? But this is the smallest way a compound can appear. And obviously, compound means 2 or more electrons or more elements coming together. So this is an element, hydrogen is another one. So here we have like hydrogen and oxygen. That makes a compound. All right, good. But what's the name of the bond? Covalent bond, right? All right. So looking at this now, this is oxygen again. This is another oxygen. Oxygen and oxygen can also form a molecule. Now, this is an element and another element. They can form a molecule, all to achieve their octet balance states. Now, how will they do that? The same way that oxygen and hydrogen did in the previous slide. So you can see both of them, and you can see again how the electrons are arranged. There will be single filling before there is double filling. So if an element has 6 electrons in the outermost shell, it's going to be 1, 2, 3, 4, 5, 6. You don't fill double at each point. You fill single first before you double. Now the same way, look at it. Now, so if these elements want to form, if they want to form a molecule together, what is going to happen is this. This is going to share with this. This is also going to share with this. So look at what we have. Here they just came closer and they shared with each other. Now, when we want to count here, they are both stable now because we are going to count it as this. 1, 2, 3, 4, 5, 6, 7, 8. They are sharing it. If I'm holding your hands, I have what you have. I have access to what you have. That's the meaning. So even though it's not like they took possession of it, but they are sharing it. They are making a bridge together. So they are both balanced. Now, this point, this is oxygen. At this point, it has formed a bond, and we call it a double bond. Now, it's going to be O2. Do you remember I told you how many bond is needed to form how many electron is needed to form a bond? 2 electrons are needed to form one bond. So if I need to form 2 bonds, how many electrons do I need? I need 4 electrons to form 2 bonds. So 4 electrons we form 2 bonds. If I need to form 3 bonds, then I need 6 electrons. So look at oxygen here. Oxygen molecule form 2 bonds with 4 electrons, right? Now, so it is a double bond here, and this is oxygen molecule. The same thing can happen to hydrogen, and it will be like this: hydrogen, then another hydrogen, right? Then they can form a bond, and you're going to have this and this, and it will be 1, 2. So this used to be H, which is hydrogen element, and here is going to be H2. So that's a molecule. So when two elements of the same compound come together, when two same elements come together, they can form a molecule, right? So this is what I was talking about since I've been talking about ions. An ion is an atom or molecule that has either lost or gained electron. I'll be talking about that, but think about what I've told you before. Ions, it has either positive or negative charge. That is an ion. Any element that has a charge on it is an ion. Now, what makes them to have a charge? That is what I'll be talking about. Now, ions with opposite charges will attract and form ionic bond. I'll be talking about that. Don't forget we've talked about covalent bond, covalency, cooperating, sharing bond. That is covalent bond. Now, when an element loses an electron, it becomes a positive. Now, I will explain. When an element loses an electron, it will become a positive charge. And when it is a positive charge, we call it a cation. Cation. You remember that cation, right? Cation. Now let me say that. Now, I will explain, okay? So don't worry. Then when an element gains an electron, it will have a negative charge, and we call it anion. Now, let me explain what that means. I said that when an element loses an electron, it becomes a positive charge, right? Why? Electron is negative. Think about it. If you lose some credit on your credit card, then you are not in debt. If you pay up, if you have some negative, let's say you bought a car and they said, okay, now you are going to pay $5,000 for the car. At the time you are leaving the dealership, you are owing $5,000. If you are losing that $5,000, the more of the $5,000 you lose, the more positive you become. Because the more of your debt you are losing, the more free you become. Your vehicle is negative at that time because you have credit with the dealership. You are going to pay the credit on it. You still have debt on it. It's a debt. But when you lose that debt, you become positive. So that's the way it is too. When you lose electrons, you become positive. Right? Because electron itself is a negative charge. So when you lose negative charge, you become positive. Let's say you have you are owing a debt of $20 and you lost the debt. Right? Then you are no longer a debtor, you are no longer negative. All right. So when an element loses an electron, it becomes a positive, right? And the positive is called cation. All right. Then negative is when you gain an electron, you are gaining a negative, then you are becoming an ion. All right. So now look at this. Sodium. You remember sodium have 11 electrons normally. 1 is here. If sodium wants to be balanced, what sodium will do is to give out the 1. Now, think about it. Sodium needs 8 to be balanced, but it only has 1. Then it's easy to give out 1 than to gain 7. Nobody is going to give sodium 7, but sodium can give out his 1 easily. On the other hand, chlorine has 7 outside. It has 7 electrons outside. All chlorine needs to do is to get 1 from sodium. This is not sharing. This is transfer. Sodium is giving its own electron to sodium. So which one is losing electron? Sodium is losing electron. And when you lose a negative, you become a positive. So sodium is going to be from here. Sodium is going to be Na. How many electrons does it lose? It lost 1. So we are going to put 1. So it means sodium became Na. Actually, it's 1 plus. But when it's just 1, we don't care to write the 1 there. We just say Na plus. Alright? So we just say sodium has become Na plus. But if it is 2, then we say 2 plus. But if it is just 1, we just put Na plus. Now, chlorine, on the other hand, gained a negative, is attracting the dead. And so chlorine is going to become an anion. An anion, it means it's going to have Na minus. Again, it's Na 1 minus. But we don't put 1 when it is just 1. Right? Like, my name is Mr. Hay. I don't need to say 1 Mr. Hay. Right? Good. But if there are 2 Mr. Hayes here, then we say, oh, there are 2 Mr. Hayes here, right? Good. Now, so you can see sodium became Na plus by losing a negative. Then chlorine became Cl minus by gaining a negative. Now, the explanation of that is this. Chlorine is saying, normally, I used to be Cl. But now, I am balanced. I used to be Cl with 2F7. But now I have 2F8. So if it is just Cl and I see Cl, I will say, oh, that's chlorine, 17 electrons. But no, it has 18 electrons now. So, but the moment I see Cl minus, it tells me that chlorine has gained 1 electron from someone else, from another element. Does that make sense? So when I see Na plus, it automatically tells me that no, this is sodium. Because if not, I would take sodium to be argon. I think argon is number 10. If the plus is not there and I don't see any electron, I will say, oh, sodium is argon. But sodium now, it has 10 electrons, but it is not actually 10. It has 10 because it lost 1 to chlorine. So when I see Na plus, it automatically tells me that, okay, this is sodium. The new electron number is 10, but it wasn't 10 originally. The plus tells me that it is 10 now because it has given 1, lost 1 to another element. The same way with chlorine. It tells me that, oh, it is 11, it is 18 now. But chlorine was never 18. But the negative tells me that, okay, it's 18 because it gained 1 from someone else. All right. So let's go. I've used a lot of time now. So that is this kind of bond that involve transfer of electron. Meaning that there is an element that lost, there is another element that gained. This kind of element is called, this kind of bond is called ionic bond. So the bond between ions, right, is ionic bond. When it is just cooperating of the cooperation of the valence, it is covalent. Good. So we've talked about covalent bond and ionic bond. So for covalent bond, there will be a cation, there will be an anion. So when you see reaction, try to look at it, which one is cation, which one is anion. The one that lost electron is a cation. The one that gained electron is a anion. It will be the negative, right? All right. So this is covalent bond. Covalent bond is still the bond between hydrogen, right? Because they will share electron with each other hydrogen molecule. Now, we can have single covalent bond, which is what is between hydrogen molecule is just two electrons are needed to form a bond. So one electron from here, one electron from here, they form a bond. That is single covalent bond. Double covalent bond is the one you have between oxygen. I told you oxygen the other time. What do you have? This is oxygen here. I think I did one oxygen here. Good. This is oxygen here. We had 4 electrons to form 2 bonds. That is double covalent bond. All right. Then this is triple covalent bond. Usually this is between nitrogen. Nitrogen is number 7 rather. So it has 2, 5. Right? 2, 5 meaning that the outer shell has 1, 2, 3, 4, 5. Meaning that 3 bonds are unpaired. And if 3 bonds are unpaired, it can also pair with another nitrogen. The 3 of them can pair with another nitrogen to form 3 bonds. So that is triple covalent bonds. All right. Now, covalent bond, I will run through this now so that I can round off soon. It's already longer than what I expect. Now, covalent bond can be polar or it can be non-polar. Non-polar means it is the normal covalent bond. Now, when I say normal, it means it is sharing of electrons equally. Now, you have a friend and everything about you is mutual. It's equal sharing. You give some benefit, the friend also gives some benefit. You give equal benefit. The friendship is consensual. It is equal. It is mutual. It is not that someone is benefiting more than the other. Both of you benefit the same way. That is a non-polar friendship. Is a non-polar covalent bond. A kind of bond that both of them are sharing equally. That's the same thing. All the kind of bond you've been seeing between hydrogen and hydrogen, it's covalent bond. It's non-polar. What you have here is non-polar. What you have here is non-polar. What you have here is non-polar because it is equal sharing. They are sharing equally. Now, both there is a kind of bond, still covalent bond, but it's not equal sharing. Now, that kind of bond, they are sharing, but the force, one of them is attracting the electron more than the other. Now, at that point, we talk about what we call electronegative. Now, the bond between hydrogen and water that forms, hydrogen and oxygen that forms water is a kind of covalent bond. But oxygen is a negative compound, so it will attract electron more than hydrogen. Does that make sense? Oxygen have electron affinity more than hydrogen. So because of that, oxygen is going to attract more. We say it is negative. You can see here, electronegativity, the attraction of an atom for the electron in a covalent bond. So in H2O, the larger oxygen atom is more electronegative than the hydrogen atom. So O atom is slightly negative, hydrogen is slightly positive. So because of that, you can see here, this oxygen is going to attract more electrons. You can see it's going to attract more electrons than hydrogen. So we say it is a polar covalent bond. So even though they are sharing, it is sharing. It is not transfer like ionic bond. It is sharing, but then the kind of sharing is that. So it's just like this. You and your friend, you shared money. You share something together, and you decide to buy a sandwich together. Sorry, I'm talking about sandwich. It's money, right? Now, then your friend have more affinity for sandwich from Chick-fil-A. Then your friend decides to take more. Let's say you bought 3 sandwiches and your friend took 2 and you took 1. It is sharing, but someone is sharing is getting more than the other. That is, you have a kind of relationship and you know that you are the one that gives sacrifice. Your friend doesn't. That is unequal sharing. So even though it is sharing, but it is an unequal sharing. That is polar covalent bond. So let's go. Hydrogen bonds, you can just read that whole. It is easily broken. That's what you have. I have to talk about properties of water, but this easy. Hydrophobic, from the word phobic, that's phobia, right? It means there is fear. So there are some molecules that are not friendly with water, like oil, fats, they are not friendly with water. Hydrophilic, that means it is friendly, all right? So oil and water do not mix together. It means that water, because water is polar compound. Please read that up. Read the properties of water. Addition actually tells you that water adds up together. Water adds together. Addition. Water adds together. It stick together. And that's why you see, when you see water molecule, look at it. It doesn't look like they are different molecules. It looks like they are drawing together, like they are drawing, they are moving together, right? You don't see water looking like a separate molecule. Then cohesion is this. Look at it. The water will not stay. You don't get to a swimming pool and see water at the center and not touch the wall. Water will normally spread out and stick to their walls, to the container, to other components around them. So that is cohesion. All right, look at the surface tension property of water too. And I think I will quickly talk about acid and base, and I will talk about pH. Now, acid is any substance that gives out hydrogen ions, and base gives out hydroxyl ion. Hydroxyl is OH minus. Now, this will make a solution to be more basic, and this will make a solution to be more acidic. pH scale is this. Everything here is more acidic and everything here is more basic. So the higher number is basic, the lower number is acidic. This is neutral, and that's why you see that you have distilled water here. It's neutral. Now, so everything up, higher numbers are basic, lower number are acidic. Then what is a buffer? Now, a buffer is any substance that helps to resist change in pH. Now, any substance that helps to maintain balance in pH, that helps to avoid deviation either to acidic or basic, any substance that helps to maintain the pH of a substance is a buffer. So for your stomach now, carbonic acid, H2CO3 will be a buffer, right? Because inside your stomach you have a pH. Your stomach is about a pH of 2, about that, right? Now, to maintain that pH value, buffer has to act. So a buffer is anything that helps to resist changes in pH. So buffer is going to take up, so like H2CO3 now, if there is higher concentration of hydrogen ions, that should have increased the acidity of a substance or of an environment. What is going to happen is H2CO3 is going to split, and HCO3 is going to attract the hydrogen ion. So even though there is more concentration of hydrogen here, HCO3 is going to capture it, and it will not allow the pH value or the acidity to increase. The same thing if it was OH minus that was going to increase, it's going to balance it like that and not cause the cell to become basic. So I'm going to pause at that point. Just look over carbon and hydrocarbon ring, chain and ring that I have here. Then please study the functional group, and that'll be fine. Thank you. Have a blessed day, and feel free to send me emails if you have questions at any point.